So in terms of what we will be doing today, when you sample from a population. So it's important to understand where the population fits in the whole picture. So as a researcher, as I've said, so I'll just go through it so that you can actually see it here. As a researcher, your interest is in the population. So whatever you want to study will be occurring in a particular population, and you'll identify the population based on what you want to study, and maybe some of the boundaries around that population, such that you can have a criteria to say which observations or which units can be included as part of your population. Then based on that, you can be able to say, this is the size of my population. You can have an estimate. Sometimes you can have the actual size of the population. But in most cases, we're not able to measure all the observations that are occurring in that defined population, such that we have to select a sample. And as you will see when we proceed, also it's more often we don't really need to observe all the units of the population for us to be able to estimate what we need to estimate. We can estimate what we want to measure using the sample, and not have to actually select all the units that are in the population. So your interest is in the population, and then because the population is too big, you select a sample, or because you can actually measure what is occurring in the population through a sample. It would be more efficient to measure what is occurring in the population using a sample. So you end up having a sample. So this sample, you are using it to do what? To get a picture of this occurrence that you want to measure in the population. So the sample is your means to the population. Your interest is in the population. The sample is your means to the population. It's therefore then important that the sample is representative. If it's not representative, then it's not going to actually mirror what is happening in the population. So from what you are getting from the sample, you want to make generalizations, what we call inferences. That is why we then have statistical tests. So from what you are getting from the sample, you want to make generalizations, you want to make inferences, you want to take what you are seeing from your sample and you want to paste it on the population and generalize. So in their population, you have parameters. So what we measure from the population, we refer to that as parameters. So the mean, if it's a population mean, it's a parameter, and it's going to be a value that we calculate from all the observations. So if we are calculating something from all the observations that are within a population, that will give us a parameter. It's going to be a value, and the value is fixed because it's a true value. If you measure all the observations, you will get the same amount, given that what you are using to measure is reliable, but it's a fixed value. What is happening in the population is a fixed value. It's a fixed value, yes. So, and it's true. But because the population is big, in most cases, we don't get the opportunity to actually examine the entire population. So we don't really have that measure. The measure is there because that thing is occurring, but we haven't been able to actually measure it, the population value, because we haven't had access to, or we haven't been able to measure all the units that are within that population, but that value exists. It might not have been measured, but it exists. So what is those values, the things that we measure from the population, we call them parameters. And then on the other hand, what we measure from our sample, So as I've said, we select a sample so that we can be able to get to the population. So what we measure from the sample that we would have selected, we refer to those as statistic. So if we calculate an average from the sample, then that average will be referred to as a statistic because it was calculated based on the sampled observations. Because it's calculated based on the sample observations, it will vary because if you select a sample and you go back to the population and select again a sample following the same principles, you're not going to get an identical sample such that for every sample that you select, if you calculate the average for the different samples will differ because the sample is different. So what we get from the sample, it varies from sample to sample because the samples are not identical. When we sample, usually if we say we're sampling with replacement, it means that I sample, if for example, I was sampling from everyone who's attending the workshop, let's say I sample 50. What it means is I sample 50, and then when I want to sample again, those 50, I put them back into the population so that they can also have a chance of being sampled again. So some of the people I sampled the first time might be part of the second sample. So, but every sample that I select will be different, such that whatever I compute will vary from sample to sample. So we use statistics to estimate parameters. So since we're not able to measure all the observations within the sample, then we use within the population, we use the sample to estimate population parameters or parameters. So these are examples. I've already made reference to the population mean, that if I can measure all the units within my population, what I will get, if let's say what I'm computing is an average, I'm going to be getting a population average or population mean, which is denoted by mu. And similarly, if I get a standard deviation from the population, it's going to be the population standard deviation. And we can also measure proportions, which is like prevalence of something, the proportion of the observations which have a certain attribute. And we can also look at correlation. So that would be a population correlation. On the other hand, when I measure them from the sample, as I've said, there will be statistic. And then if it's an average, it's going to be the sample mean. And we represent it using what? X bar. And then if it's a standard deviation, it's going to be a sample standard deviation. We represent it using S. So these also representations are also important so that when you also read through statistic material, you're also able to understand when they put mu, they are talking about a population. When they put X bar, they are talking about a sample average. So I think even to familiarize yourselves with the samples, the symbols that I used is also important because it says that when you are if you have a textbook and you are reading about some of these things, they will make better sense to you because you also understand the difference between these symbols that are being used. Some are used to refer to a population, observation calculated. Not observations, but things that we calculate from the population, measures that are calculated from the population, yes. And then others are used for measures that we calculate from the sample. So I've said because we are sampling, if we're doing a study, an experiment, it will be conducted on a particular sample. And as I've said, because the sample, they are different, there is a possibility for any sample when you draw the sample. And we make inferences based on the samples that we would have selected, such that it's important that the sampling is also sound, so that the inferences that you made can also have a theoretical backing. Usually we say a probability sampling techniques, we advocate for that wherever possible, but the reality is when you actually have to sample, sometimes you cannot select a probability sample because of you don't maybe have a frame, a sampling frame, or maybe the sampling frame is not, the coverage is not fine, or it's not up to date. So in real life, it's not always possible to select a sample using probability sampling techniques. But the thing is, when we use non-probability sampling techniques, some of the theoretical properties that are required for sound inferences are lost. But we are still able to make inferences. However, the inferences, you have to make them correctly and be aware of the limitations. So in terms of sampling, when you are doing a study, your research, whether it's experimental, whether it's an observational study, careful planning is required. It's important that your problem is defined properly and you operationalize it. So you take it from the theory or from the concept to a practical approach, as to say that for my study, this is how I'm going to be measuring the variables. So you start from a theoretical point of view to say, when we refer to high blood, this is what we mean by high blood pressure. It's got this and that, and then you get to a point where you tell us that for your study, this is how you're going to measure it, if it can be measured in more than one way. So you when you operationalize it, when you get to the point where all your variables that you want to collect, it's clearly defined as to how you are actually going to measure them for the purpose of your study, taking into account the resources that you have. So the resources, it's all inclusive, the time, the money, equipment, your skills. When I talk resources, it's inclusive of everything that will go there. And when you operationalize your problem and you define it correctly, you'll also be able to see in terms of the method, which kind of a design you will be following. Are you able to do an experiment? So let's say, for example, you want to you are a lecturer or you're a teacher, and you are involved in design, curriculum design, all those things, and there is a new teaching approach that you have developed and you want to test it. So you want to do a study to test the teaching approach. So maybe it's gonna involve, it's some form of an experiment, but you might not be able to control some of the independent variables, such that even though maybe it has got some aspects of an experiment, such that maybe you put some learners, they use the old teaching approach or the standard approach, and then you have so there would be the control, and then maybe you also have other learners who are assigned to this teaching, the new teaching approach. So it is some form of an experiment, but you might not be able, as I said, to control other external variables. So maybe it will be a quasi-experiment. In other cases, you can have a true experimental design, or you can have an observational study. So as you carefully define it, it will also lead you to be able to select the correct, to be able to say that my study is observational and it's cross-sectional, or my study is observational and it's longitudinal, because I have to measure whatever I'm measuring, I have to measure it more than once. So once I'm measuring more than once, it will become longitudinal. So then you need to select your units from the right population. If it's an experimental design, proper randomization, and you follow procedures properly, you need to be able to. So these are some of these things. They feed into your sampling. The number of variables you need to be aware, and the type. So in terms of the type, the scale of measurement is very important. We have spoken about that in previous workshops. So you need to be aware of the scale for your outcome variable or your outcome variables and your independent variables. So you can see that this thing of scale of measurement in quantitative studies, you can really not run away from it. It just appears everywhere. So it's important that you get a good understanding of the different scales and the properties or the characteristics of the different scales, so that you'll be able to make, even when you estimate the sample size, this is also important, so that you'll be able to use the correct technique to estimate the sample size. And sample size determination is very important when you are doing a quantitative study, because if the sample is not enough, then you might not be able to pick up the differences that you wanted to study, because the study does not have enough observations, or other statistical analysis techniques require large samples. So if you selected your sample is small, then you now start to have limitations, because your sample is small, but the statistical technique that you need to use requires a big sample. So sample size determination is an important component of your proposal or the planning of your research. So we want to provide accurate and a practical way to enable inferences, because we say that we want to make inferences, take what we see from the sample and paste it on the population. I've already said that the sample has to be adequate. That's why we have sample size determination techniques, and it has to be enough in relation to the objectives of the study. So it's not like a blanket approach, but it's always in relation to the objectives of the study. And it must not be too big, such that an effect of such magnitude as to be of scientific significance will also be statistically significant. So if you have a big sample, you are likely to find significant differences, even though they are not maybe really there. So it must not be too big. And also, the other thing is that when it's too big, the sample must not be too big, such that an effect of little practical importance is statistically detectable. So as you will see as we proceed, there is the statistical significance, there is also practical significance. So you find that the sample is too big, and because it's too big, you do find a statistical significant difference. But in practice, that effect, the difference now in practice, they are of little practical significance. So even though when we do studies, other researchers don't get to that point where you actually think about what the results, what they mean. For example, if I go back to this example about a teaching method, if the teaching method, maybe for example, it is costly, so you will have to look at, if when you are comparing the two groups and you get that there's a difference, you also now want to look at how big is this difference. If the difference is not that big, yes, even though it's statistically significant, but if the difference in practice, it's not that big, and you look at the amount of money that will be spent on this method, then you start to weigh, to say, is it really worth it? Yes, the results are saying there's a statistical significant difference, but practically when I look at this difference, it's just practically doesn't really add that much value. So there is always that aspect of, when you are doing a study, at the end your results have to translate to practice, to say in practice, this differences or this effect, what difference does it make? Does it change people's life? If it's if it's high blood pressure, if it's reduced by 2 units, 5 units, clinically, does it make a significant difference in a patient's life? So there are always those two things. As you will see as we proceed, we will go into them in detail. Yes, so when you have a sample that is too small, it's not going to be enough to be able to detect the differences, even though they are there. And you are also in maybe clinical studies, perhaps this new treatment that you are testing, perhaps it's got side effects, severe side effects, and you are doing this study that is underpowered, and you are exposing participants to this treatment that has severe side effects, but there is no new knowledge generated because your sample is not sufficient. And also, on the other hand, if you have the sample is too big, then you can also expose a high number of participants to, if we go back to side effects, unnecessarily, because the sample it's more than enough. So you are exposing more participants than necessary to this new treatment that has some side effects. Or you are also denying the other group a possibly beneficial treatment. So there is that balance, that the sample must be sufficient, must be adequate, and you can follow the different techniques to work around a sample that is sound as per the different inputs that you consider when you select the sample. So going back to where we want to go, we have a population, what we are studying is in the population, and as part of our problem or our question, when we phrase our question, we hypothesize something about that particular phenomenon that is happening in the population. So there are claims that we are making as researchers. As you approach the problem, you will have some claims to say, what I'm observing is the prevalence of teenage pregnancy is high in this particular population. So that's what you want to study. So there will be some claims about the population. So those claims, you can refer to them as hypotheses. Very important. The hypotheses are about the population of interest. So it can be about a parameter, as I've used a teenage pregnancy, population teenage pregnancy, the prevalence is a proportion. So it will be the population proportion. It can be a relationship between two populations. So a claim that I can make, I can say, remember these claims here, I'm not talking about the null hypothesis, the alternate hypothesis. At this point, it's just claims that you are making, as because maybe you have some data, underlying data, or you are working in that particular environment and it is what you are observing, and you probably have some figures, even if maybe they are not adequate, but they are giving you indication that perhaps the prevalence of teenage pregnancy in area A is higher than in area B. So that could also be a claim. So now it's about these two populations, that the prevalence of teenage pregnancy in area A is higher than in area B. So maybe that's what you are observing. And as you do your study, it will be one of the claims. And yeah, so those are some of, so the claims are about what is happening in the population. It's got nothing to do with the sample, but the claims are about the population. So for example, here we talk about, you will maybe say from a random sample of learners, you are claiming, so when you are testing it, you will test it maybe from a random sample, but you are actually claiming that the population IQ is 100. So that's what maybe you are an educator, and it's what you are observing. So you are claiming that the population IQ is around it's 100, and then you will use a sample to actually see if there is evidence. But your claim, the sample comes in as what we will be using to gather evidence. But the claim is about the population. And going back, you have area A, area B, are there differences there? So you are making claims that there are differences. The sample will come in as a way to say, do we have evidence? And then I've used the example of prevalence before. Here it's smoking. So it's also a claim that you are making. And then the sample comes in now as what? As what you will use, what you collect from the sample, you will use that as evidence for these claims to say, these claims, how true are they? So now when we come to hypothesis testing, when we now test this hypothesis, we will be testing them statistically. Once we test them statistically, we present them in the form of the null and the alternate hypothesis. So you take your general claims that you have about this population of interest, and then you will phrase them in the form of the null hypothesis, and then you will also have the alternative hypothesis. So the null hypothesis in statistical testing is the hypothesis that we are testing, and it's denoted by H0. So when you see H0, you know it's the null hypothesis. As I've said, it's a statement that we make about a population parameter, not population mean. Yeah, it's about a population parameter. So if you look here, underneath there is the hypothesis X bar. If we go back to at the beginning when we were speaking about statistics and parameters, I said you must take note of the symbols that are used so that when you see it, you can also be able to say if there is something wrong. So here, this null hypothesis would be incorrect because it's talking about a sample. It's talking about a statistic. It's talking about a value that is computed from the sample. X bar is the sample mean, which is computed from the sample. And also we don't have to do this because when I have a sample, I can compute the sample mean and I will know it. For that particular sample, I can compute the mean and I will know it. But what I want is what is happening in the population mean. So my null hypothesis has to be about the population. So in this case, it has to be about the population mean. So we test whether the value that is stated in the null hypothesis, how likely it is to be true. So this is just more elaborate, like more explanation to say how likely are these results that we are obtaining from the sample likely if we assume the null hypothesis is true for the population. So I will give some examples of the null hypothesis and it will make sense. So our statistical tests, we are about the null hypothesis. The null hypothesis is about population parameters. So when we state the null hypothesis, we will be saying something about the population parameter. So a null hypothesis is silent. So when you put your null hypothesis, the null hypothesis is silent. It doesn't favor any group. That's how you put the null hypothesis. Because if we go back to the example, I will use this example for as long as it's relevant of the teaching method and a standard method. When I'm doing the study, it is because I have reasons to believe that this new teaching approach is better. I believe that it's better. So when I actually compare it, I'm hoping that my data will provide evidence to say that the new teaching approach is better. But how you put the null hypothesis, you will say that the two approaches are the same. So you will not say this one is better. In the null hypothesis, that's why we say it's silent. It will say the two methods are the same. So it's not going to favor any group. So the null hypothesis states that there is no difference between a parameter and a specific value, or that there is no difference between two parameters. So exactly what I'm saying, if it's two groups, you will say that they are the same. If the study is about relationships, correlations, then we say the null hypothesis will say that there is no relationship. So the null hypothesis is silent because we want to use our evidence that we gather from the data to actually reject it. So in hypothesis testing, the hypothesis testing is about the null hypothesis. We want to use the evidence that we are getting from our data to reject the null hypothesis. The null hypothesis, if we go to my example of the teaching methods, it says they are the same. When we reject it, we will be saying that we have evidence to suggest that they are not the same. So we say, when we put the null hypothesis, we say the two methods are the same And the intention is to use our data as evidence to reject that null hypothesis. And when we reject it, we are saying we have evidence to say that the two methods are not the same. I hope it makes sense. And similarly, even with relationship, if it's a relationship, we will be saying that there is no correlation between weight and height. So the null hypothesis will say there is no correlation between the weight and the height, meaning that the weight and the height are independent. That's the other way. And then we want to use our data as evidence to reject that null hypothesis. Once we reject it, the null hypothesis says there is no relationship or there's no correlation. Then when we reject it, we are saying we have evidence to say that there's a significant relationship between those two. So we use probability theory. But there is always a chance that we can make incorrect inferences. So there's a chance that our conclusions can be incorrect. So such that maybe we reject the null hypothesis when we are not supposed to reject it, or we don't reject it when we are actually, supposed to reject it. So we have the null hypothesis, then we also have the alternate hypothesis, which will be a statement that directly opposes the null hypothesis. So our statistical tests about the null hypothesis, but then we have an alternate hypothesis which will oppose the null hypothesis. Yes, so in the example of my teaching method, my two teaching methods, a standard one and a new approach, the null hypothesis says that those two methods are the same, and the alternate hypothesis will say they are not the same. So there are two ways the alternate hypothesis can be put across. One way is to say they are not the same, and you are not actually saying which one is better. You are just saying they are not the same. That we say it's a two-tailed approach. And then the other way would be to say method A is better than method B, or method B is better than method A. In most cases, when we do a statistical test, we go with they are not the same. But in other studies, when you do have evidence to actually put your alternate hypothesis in a certain direction, so meaning that you say this one is better, or this one, one of them is better, you can do that if you have evidence to take that approach. As I say, in most cases, we follow a two-tailed approach. Yeah. So there are two examples here. If we toss a coin has two sides. It's either a head, a tail. If it's a fair coin, we expect that the probability of getting a head and the probability of getting a tail, they will be the same. So that would be an hypothesis that we would make about that kind of an event, that kind of a scenario where if we toss a coin, we can say we hypothesize that the probability of head and tail, they will be equal, because we are assuming it's a fair coin, it's not biased. Then the alternate will be that the coin is actually not it's not unbiased. And then the other example is here. If we have a new treatment for high blood pressure that we hope it can reduce high blood pressure, and you are measured as a patient, they measure your high blood pressure before you go on the treatment, and they also measure the high blood pressure after you have been on the treatment. Obviously, they will specify the appropriate time that you must be on this treatment for, and when, after how long you need to be measured. But in principle, you are measured before and you are measured sometime after you've been on this new treatment. And then there is your blood pressure that before, as I've said, and after. So in terms of the null hypothesis, we will say that for this group, for the people who have been sampled, we would say in the population, the blood pressure before and the blood pressure after, it's the same, meaning that this new treatment does not really have a significant effect. And the alternative, as I said, if you use a two-tailed, it will just say that they are not the same. So it's not going to say that the one after is more, the average after is more, but it will just say they are not the same. But if you have evidence to actually do a one-sided test, then your alternate hypothesis will say maybe that the average, the population, the average after is more, is less, because it's supposed to reduce in this case. So it's going to say it's less than before. So it's always also in line with what you are trying to do here. What came to my mind was to say it's more, but in the context of this study, we are expecting the high blood pressure to go down. So the one after, we expect it to be lower than before. So the decisions that we make in hypothesis testing, they're around the null hypothesis. Null hypothesis is not really a formal proof that the hypothesis testing is not really a formal proof that any hypothesis is true, but it's based on evidence. So I think that's the other thing that you must take away from this, is that it's based on evidence, the evidence that is presented. The decisions that we make are based on this evidence that is presented, which is the data that we've collected from our sample. So our decisions are based on the data, the evidence. So we always use the analogy of a court case to say that when someone has committed an offense, or when someone appears in court, the reality is that in the real sense, the truth is there somewhere. The truth of whether this person has committed that particular offense or not, the truth is there. This person has either committed this crime or they have not. The truth is there. But now when we come to court, decisions will be based on what? On the evidence. So the same principle applies. In hypothesis testing, decisions are based on the evidence presented. And with the court case, it is possible that based on the evidence that is presented, the court can say you are guilty while you are actually innocent. Or the court can say you are innocent while you are guilty. But the truth is there. The outcome, the court outcome, are based purely on the evidence. And for the particular court setting, the court assumes that you are innocent, and the evidence that is presented, it's the one that's supposed to sway the to change that position of you being innocent. So it's the evidence that is presented. But as I say, based on the evidence, the court can say you are guilty when you are innocent, or they can say you are innocent when you are guilty. The court would like to be fair, and the court doesn't want to punish people who are innocent. So between those two mistakes that I've highlighted, they would rather say you are you are innocent while you are guilty, as opposed to say you are guilty while you are innocent. They wouldn't want to punish people who are innocent. They'd rather, say you are innocent while you are guilty. It's more of the mistake that maybe a better mistake that the court would live with than the other one. So similarly, so I'm laying a foundation with this because your understanding of why are we doing a test and some of these things that I'm introducing as we go through this are elements that you need for you to estimate the sample size. So you need to actually understand what they mean. So this takes us to our setting when we do hypothesis testing, drawing from this analogy of a court setting. As I have said, even with us, we are doing hypothesis testing. Hypotheses are around the null hypothesis. And we also want to use evidence to make decisions. And our evidence in this case, it's the sample data. Even with us, in our hypothesis testing, we can commit two types of error. We have type 1 error, we have type 2 error. So type 1 error is if we reject the null hypothesis when the null hypothesis is true. So as I've said, if we go back to our example of the two teaching methods, our null hypothesis says that they are the same. So when we reject it, what are we saying? We are saying we have evidence that they are not the same. If we go to maybe high blood treatments, if we reject the null hypothesis, we are saying the two treatments are not the same. So in that decision, we can reject the null hypothesis incorrectly when it's actually true. When it's true is when they are the same. If we reject it, we are saying that they are not the same. So that is one error that we can commit. And the probability of committing that error is referred to alpha. So you can see the alpha here. It's referred to as alpha. So alpha is the probability. The actual error is inside the brackets. So the error that the type 1 error is inside the bracket, which is we reject H naught when H naught is true. We actually want to reject H naught when it is false. But we reject committing a type 1 error. And the probability of committing that error is referred to as alpha. We also say its level of significance. That probability is usually chosen to be 0.05 or 0.01. So we set it. We decide that how much error, how much type 1 error are we willing to accept. So as I said, we usually work with 5% or 0.05. In other studies, we work with 0.01 or 1%. Then on the other hand, we also can commit a type 2 error. So the type 2 error will happen if we do not reject. So if based on our evidence, remember, as I say, our decisions are also based on the evidence. But in the population, the truth is there. But unfortunately, we're not able to get to the population. So we are using a sample. So in us using the sample, which is our evidence, we can commit a type 2 error, which is we don't reject the null hypothesis when it is false. When the null hypothesis is false, we want to reject it. When we don't reject it, when it's false, we are committing a type 2 error. And the probability of committing this error is denoted by beta. So beta it denotes the probability of a type 2 error. What is type 2 error? Type 2 error is if it occurs if we do not reject the null hypothesis when the null hypothesis is false. We want to reject the null hypothesis when it's false. So emanating from this type 2 error, we have what is called the complement of the type 2 error, which is what we refer to as the power of a study or an experiment. It's the probability that the effect will be detected. So what is that? The probability that we reject H0 when H0 is false. This is what we want. We want to reject H0 when H0 is false. And that probability is referred to as the power. And it is also one of the elements that are used in sample size determination. So power is the probability that we reject the null hypothesis when the null hypothesis is false. So it is 1 minus the probability of type 2 error. It's 1 minus the probability of type 2 error. So this is just a summary of the decisions we can make when we're doing hypothesis testing. 1, we reject the null hypothesis when the null hypothesis is true. So that would be a type 1 error. And it's a false positive. We are saying there's a difference when there is no difference. And then we can also reject the null hypothesis when it's false, which is what we want. We want to reject it when it is false. We want to reject it when it's false. So this would be a correct decision. It's a true negative. And then on the other hand, we can decide not based on the evidence, which is our data. We do not reject the null hypothesis when the null hypothesis is true. So when the null hypothesis is true, we don't want to reject it. So this will also be a good decision. And then the other, which is now our type 2 error, is we don't reject it when it's false. When it's false, we want to reject it. When it's true, we don't want to reject it. So when it's true, we don't want to reject it. If we reject it when it's true, it's a type 1 error. If we do not reject it when it's false, it's a type 2 error. So the probability of type 1 error is alpha or level of significance. The probability of type 2 error, we denote it by beta. So now moving on to sample size determination. So we need to, the sample that we are using, it has to be big enough, as I've mentioned, for us to be able to have enough probability of detecting an effect when it actually exists. So we say here, I said that the probability that we reject H0, when we reject H0, we say what? We say there's a difference, there's a significant effect when H0 is false. Yes, this is the power. So we want, when we do the sample size estimation, the sample has to have enough power. The study has to have enough power to be able to detect an effect when it exists. So factors that are required, or some input elements into sample size determination, is the effect size, which we will explain, which is the minimum expected difference. That is the difference that would be significant practically. Then we also need the measure of variability, and we need to be able to say whether we're doing a one-tailed or two-tailed statistical analysis. I've spoken about the power of the of the study or the experiment, and then the level of significance, which is alpha, and then there's also the margin of error. So some of these elements, they are unique to the study, and others, you fix them. So you will say for the study, I want my study to have this amount of power. I want the level of significance to be 5%. I want the margin of error to be this much. I'll go into details. And for example, the effect size will be unique. And even the measure of variability will be unique because variables are different and how they behave in different population, it's different. So the estimated measure of variability will be unique. And the measure of variability, you actually get it when you measure. So those are the dilemmas that you need to have the measure of variability as an input for sample size estimation, but you haven't actually measured. So how do you know what you can use as an input? So picking up from those factors, two approaches can be followed generally when we do, even though there are other different approaches. Other approaches are about, they will say that if you are doing linear regression, you need to have 10 observations per variable. So there are also those generic guidelines. This is when you are estimating the sample size for yourself. So we have a power-based approach and a precision-based approach. If you're following the power-based approach, we use this effect size, which is the minimum expected difference. We will elaborate. I spoke about measure of variability, whether it's a two-tailed or one-tailed, and the power, you need to specify the power and the level of significance. If you're using a precision-based approach, you will have to specify the margin of error, the measure of variability, whether it's two-tailed, and the level of significance. So I'm just gonna go through this now. These elements. Others I've already spoken about the power and the level of significance. So I'm gonna rush through them, and then we'll touch on the other ones that we haven't touched on. So we've spoken about the power. It's a probability that you reject the null hypothesis when it's false. So that's what we want. We want to reject the null hypothesis when it is false. So we conclude that there's a difference, a significant difference when it's actually there. That's what we want. So we want our study to have enough power. And as I have said, the power, if we come here, you specify to say, I want my study to have this amount of power. So if I use an example of males and females with regards to IQ levels, if I'm comparing them, the null hypothesis will say what? The average IQ for males is the same as the average IQ for females, meaning that if I subtract, I will get a 0 difference. Then if it's two-sided, I will say they are not the same. If it's one-sided, I will either say males have higher IQ, or I will say females have higher IQ. So I think you can also see here the one-sided and the two-sided. So the power has to be enough for us to detect a difference when it's really there. So here, if there is a difference here, we want our study to actually have enough power to be able to detect this difference. So if usually 80%, 0.8 is used in most studies as the power, the amount of power, the desired. And we saw in the previous slides when I introduced the errors that the power is 1 minus the probability of type 2 error. It's related in this way. So when the power is 80%, there is a 20% chance that a type 2 error will occur, because this is how they are related, right? So if the power is 80%, then there is a 20% chance that a type 2 error will occur. That the probability that the null hypothesis is not rejected when it's false, it's going to be 0.2. So I hope it makes sense, because they are related in this way. When the power is 80%, then we have 20% chance that a type 2 error will occur. So if we go back to our males and females IQ levels, if the test, let's say the decision is that we do not reject the null hypothesis, so it's saying there are no differences, right? If based on the data that we would have collected, we come to the decision that we do not reject the null hypothesis, it's it's possible that there are no differences, which means that our test gave us the right thing. It's also possible that the result of no difference is false. So the difference is there, but the study was not powerful enough to detect the differences. Remember, this is in relation to saying that given the opportunity to actually measure the entire population, the true value is there. But now, when we make decisions based on our sample, which is our evidence, these are the decisions that we can make. We can find that our study did not have enough power to detect a difference, even though it was there. Then this would be a type 2 error. So we need to have enough power so that we can say there is no difference when there is truly no difference. So in terms of the power, some summary in terms of the power, it does depend on the variability, and it increases when the variability is less. When we increase the probability of type 1 error is increased. If we increase the level of significance, and then if the effect size is larger as well, if you do a one-sided tail test, the thing with the one-sided tail test, you need to do it when you have evidence, because it only evaluates the site that you have specified. So it will just say, if it only looks at that site, it doesn't look at both sides, it only looks at one side. That's why you only have to do it if you have evidence to take a side, because it's not going to pick up the other side that you have not specified. Such that also with the power is related to our sample size. So if the study is underpowered, we might not be able to detect meaningful differences. And if it's too large, the study can also be overpowered. So if we want maybe to see there is a trade-off between type 1 and type 2 error, if we keep other things fixed. So for example, if we say the power is 80% or 0.8, and our level of significance is 5% or 0.05, we can say that the type 2 error is 4 times the type 1 error. So there is that trade-off. So moving on to the statistical significance. Statistical significance, we said, is what? Is a type, it's alpha. It's our level of significance, it's alpha, which is the probability of type 1 error. Statistical significance is alpha, which is the probability of type 1 error. We also call it level of significance. So we're usually interested in comparing groups or we interested in relationships between variables. We want to know if there's a significant difference between these groups, or if there are significant relationship between the variables that we are looking at. So significant is with reference to the null hypothesis, which says there is no difference between the means, or there is no relationship between the variables. So we usually reject the null hypothesis using the cutoff point of 5% or 0.05. That's when we will conclude that we reject the null hypothesis when the p-value would have computed from the test is less than this level of error. We are willing to accept. Remember, it's type 1 error is an error. So we say we are willing to accept 5% of an error, and we are saying that 5% of the time we accept that we will make a wrong conclusion. Yes, so I've said that it's a level of significance. We say it's statistical significance, which is alpha. The probability the null hypothesis is incorrectly rejected. We want that probability to be small. Remember, I said that it's an error, so we want to keep it small. The probability that we incorrectly reject the null hypothesis, meaning that we reject the null hypothesis when it is actually true, we want to keep it small using the 5% cutoff point, and in other studies we use 1%. Yes, so once we do that, the null hypothesis says there are no differences, relationships found in the probability samples are not due to simple chance. So we don't want our conclusions to be due to chance. Chance means that we just so happen to have a sample that is giving us what we are observing, but it's not a reflection of what is happening in the population, and we want that chance to be small. How small? We want it to be less than 5%. And then we move to practical significance. So I said there is the statistical significance, and I used the example that sometimes the results will be statistically significant, but then you need to now, because these results, they talk to a real life situation. So in terms of practically, when you look at the difference or this effect, is it practically significant? So the statistical significance doesn't tell us how important the differences or the relationships that we are picking up at. So when do we say a difference or relationship is big enough or large enough to be considered important? So practical significance is about the size of the effect. So when we say that the treatment has a significant effect, what is the size? Is this effect small or is it big? And as I say, practically, does it really add value? Does it improve whatever it's meant to improve? If it's 10%, does it actually change things in the bigger scheme of things, or does 10% not really change this particular thing that we are studying? So what we get from testing the null hypothesis, we don't really get that to say practically is this effect significant or not. So in terms of practical significance, your knowledge about the subject matter, your expertise, you can use that to be able to say, I mean, if we say the blood pressure is reduced by 1 unit, it actually does change someone's life, or actually it doesn't really, for us to be able to start to see a difference in the quality of life, maybe the difference has to be 10 units. So I'm just using this as an example. I'm not saying that's the case for high blood pressure, but I'm just using it as an example. you can say that. For other things, it can be said that 1 unit is actually enough practically to actually improve the quality of your life. So practically, because as I say, you are doing the study, but this study has to translate to something meaningful in relation to the population that you are studying. So you also have the practical significance when we do the sample size estimation that we also have to consider. So as I've said, you can use your expert knowledge to be able to say what is practically significant. And so the effect size, that's what we call the effect size. And there are indices that we can use. There are formulas that can be used to compute the effect size. When you analyze your data, when you do a statistical test like a t-test, for example, in SPSS, when you have collected the data and you do the analysis, you can select the option that it must also give you the effect size, so that once you see that there's a significant difference, you'll also be able to see practically now or clinically if this effect is significant or not. Then you can look at the effect size, the indices, and analyze that. I'm not going to go into that, but I think I'll go into it just a little bit, but I won't go into the formulas. Yeah, so the index has to be large enough. There are different cutoff points. In clinical trials, that would be called a clinical significance. So in terms of the effect size, we can have, there are 2 families. There are those which are computed when our study is about comparing groups. For example, I think I used the example in this example where we are comparing a standard treatment, and we're also comparing it with a new, like a standard teaching approach. We're comparing it with a new teaching approach. And even with categorical data, we can be comparing pass, fail for different groups of students. So it's not only for continuous. When we say groups, it can be things that are measured numerically or are measured categorically. But whenever we are comparing groups, whether we're looking at the odds of passing for the odds of passing if you are on this teaching method as opposed to when you are on the other teaching method, we are also comparing groups. And the other one, I mean, with the same thing, it could have also been measured numerically, whereby we have an assessment and we actually use the actual marks, the average. Not necessarily, we don't convert it into pass-fail, but we analyze it as an average. And then on the other side, we have the family that looks at relationships or associations. So that would be the R family. So when we talk differences between groups, that would be the D family, as I've said, can be continuous or categorical variable. I've already said if you're looking at pass, fail, that would be like a binary, and maybe comparing it for pass, fail for those on this method versus those who are on the other method. You would be using, you'd compute the effect size using they are coming from those kind of comparison that are coming from the D family, and one can use the Cohen's D. And then coming to the measures of association, you will have the different measures for different things. If, for example, it's just a continuous variable, you're looking at the correlation between 2 continuous variables, then what you can use to get the effect size would be the correlation coefficient. If the data is ranked, then you can use the Spearman's rho to get your a measure of effect size. So these are the ones that would measure. You'd use these are examples. There are many others actually. But whenever your interest is in relationship, correlation between variables, then you will use the effect size measures in this family. These are the examples. So I've used also this one. It's about context to say if contextually, how many units do you need to be reduced of blood pressure for you to say that the effect is actually practically significant or clinically significant. And then the other element is variability. So I think you remember, so that variability was one of the elements that we need to be able to, as an input into our sample size formulas or the techniques that we are using, we need to have the measure of variability as an input. So this will be in relation to the variables of interest in the study. So these are dilemmas because you need this variability, but you haven't really measured. You don't have, you haven't collected data. So how do you get this, the estimation of the variability for these variables? Because you haven't collected any data. So some possible approaches that you can use, once, let's say you can select your sample in two phases. So you just select a sample. You might not know if it's sufficient or not sufficient. So maybe you select 50 units and then you now compute. You do your computations, and from those you'll be able to get the variability. And then you take that variability as an input into your formula for sample size estimation for you to now see, now that I've collected 50, do I need more? Based on this variability that I'm getting from the 50, which I'm using as a proxy for the variability in the population, how do I need more observations? How many more observations now that I have this variability that I needed? Obviously, the other option would be to do a pilot. And from the pilot, you would be able to estimate the variability, and then you can be able to input it in the formula to estimate the sample size. We also talk about using data from previous studies where they looked at similar populations or the same population as yours. So maybe they looked at a population that is similar to yours, and this is the variability that they got in the study, and you can use it as an input now for you to be able to estimate. You can sometimes adjust it to say, in this study, this was the variability, but given these conditions, I will make it slightly bigger because my population differs slightly with this one. So I expect the variability to be higher or to be less, but you can take what you are getting from previous studies and use it. Sometimes use it directly as it is. Sometimes you have to adjust it to say, taking into account the difference between this, because the population might not be exactly the same. So taking into account certain differences, you might say these differences might make mine to be slightly higher or slightly lower. And you take that one, you adjust it, and you use it as an input for sample size determination. So when we talk about binary variables, which we measure a lot when we are doing prevalence, when you want to look at pass, fail, prevalence of something, prevalence of a disease, whether people test positive, negative, that is a binary outcome. When you cannot get it through what is suggested here, we usually use a 0.5. And I think some of you maybe who have attempted to do the sample size estimation for yourself, especially those who are doing survey research or people who are doing work engagement, all these things that are maybe sometimes under HR. You find that 0.5 is used quite a lot, because me, if I'm assisting you with the sample size, all these things that I'm discussing here as inputs, and I'm actually left with just one, I'm going to ask you, what do you expect the variability to be? And you will have to tap into your expert knowledge, or go back to the literature, or do a pilot study. But these are the things that you need to input, you need to have for you to be able to estimate the sample size. So I was saying here, this is very common in survey research, whereby someone is, say, they want to measure work engagement, and they cannot really tell you that this is the level, these are so many people are engaged, this is the estimate. So when we estimate the sample size for those kind of studies, we usually use this 0.5 a variability, and it gives us the maximum sample size. Then the last thing is the margin of error, which is an indication of a level of precision of that particular estimate. It is influenced by the sampling error and the natural variability in the population. The sampling error is more about, here is the population, here is the sample. How far is this sample from the population? That would be your sampling error. We usually use a 5%. Recently, I'm seeing a lot of 3% margin of error. But yeah, the 5% margin of error is very common. So for a binary variable like pass, fail, the margin of error means that the researcher is confident that the proportion of respondents who passed was within plus minus 5% of the proportion obtained from the sample. So from the sample, you will get a proportion of those who pass, those who fail. So you'll get a proportion of those who pass. And that proportion, if we're using a 5% margin of error, we are saying that we are confident that the true value of the population, meaning the proportion of those who passed, is going to be what we've estimated plus minus 5%. So if we use this example here, if we look at customers, if we wanted to look at customers who prefer a certain brand over another, the results, suppose the results, they say 80% of the participants prefer brand B, right? So we do a study, we select a sample, and the results say that 80% prefer brand B over A. If we were doing, the margin of error was 5%, then we are actually saying that the true value is between 75 and 95%. So the true value of the people who prefer brand B is between this range. So you can see that when you make the margin of error bigger, your level of precision will be reduced, because if, let's say, instead of using a 5%, I use 10%. So you can see that this bracket here, I still have 80%, but my margin of error was 5%. Then it would mean that this now becomes, this interval will be 70 to 100. So it's wider. It becomes wider. So once it becomes wider, my level of precision is reduced. When it's smaller, and it's between 75 and 95, it's a smaller interval. But 70 and 100, it's bigger. So it can be anything in that range, the true value. So it's now bigger. It's no longer that precise. So when the margin of error, when it's large, your level of precision is reduced. And But with when you have a high margin of error, the sample size required will also be higher than the one required for when we reduce the margin of error. Yeah. So I'm gonna pause here, and then we didn't talk about the break, the time. We're gonna now be moving into the actual computations. So I think we can take questions now. And after the questions, I'm not sure how long we can entertain the questions for, and then we can take a break. Thank you, colleagues. I hope you are back. And I hope you've attempted the quiz so that we can just, apply our minds to what we've been discussing. So in terms of the first question, the question says, suppose we want to do a survey on CGS M&D workshops, and I select 50 master students, or 50 master students are selected for the survey. That's the assumption. What is the correct population? So these M&D students, they are coming from a certain population. And I think what is important here, you have to look at what are you studying? What are you studying? The study is about CGS M&D workshops. So if we assume that for you to participate in the study, you need to have knowledge about the workshops, then you cannot be part of the population if you don't have knowledge about the workshops, right? You must have attended at least one, or maybe there will be a criteria, but you must have the knowledge. The study is about CGS M&D workshops. So if we're going to ask questions about that, the people that we are targeting have to have the knowledge. So that is a starting point to say. So in terms of the response options, UNISA M&D doctoral students, if the questions will be asking, you need to have knowledge, as I've said, about the workshops. The entire UNISA M&D students would not be appropriate, because it doesn't mean that you are a UNISA student. You've actually attended one of the workshops such that you can be able to respond, because you can only be able to respond if you have knowledge about what you are being asked about. So it excludes the first one. Then the second one, UNISA postgraduate students, given the explanation I've provided, it's also excluded. All UNISA master students, it's also excluded, right? Because it doesn't mean that you are a master student, you've attended. So it is none of the above, because you need to have the knowledge. So obviously the question didn't have the details, but these are some of the keys that you have to, obviously someone can motivate to say, no, even though the workshops are about CGS, for my study, you don't need to have attended the workshops. So if you motivate and you provide a justification, then the UNISA master students can be a population. But if the study taps into, you must have attended, like for you to respond, you need to be providing information about the workshops. You are reflecting on the workshops, you must have attended. So none of the above. Then we've come to the second one. It's the same thing. We're doing a study, same, but I select 50 master students. What is the sample? The sample will be 50 master students. That's what I selected. So that would be the sample, and I'm saying I selected. So I sampled. So most of you got that one correct. And then number 3, we are measuring IQ levels of UNISA students, and we obtain the average IQ. The IQ obtained is what? So the IQ that we have obtained is it's a parameter, because we've measured everyone. So we've measured everyone who is a UNISA student. So whatever we've measured from what? From the population, because we measured everyone. And I think you can see that this context is about students. So we measured all the students. So the average IQ that we will be computing, it's based on the population because we measured everyone. So it's a parameter. And then we say a statistic is computed from, it's computed from those who said a sample, they are correct. Because we say that from the population, we get parameters. And then if we're using sample data, we compute statistics and we use them to estimate population parameters. So yeah, 73%. Number 5, so when we the measurements that we compute from the variables that are measured from census data. So census data means what? We're not sampling. So we're measuring everyone. So there would be parameters because we're measuring everyone. They are parameters. We're measuring everyone. If we do a census in South Africa, they do a census, they count everyone. That total, they've counted everyone. If they estimate if they say so many people live in these types of houses, so many people have got access to tap water, they've measured everyone. And then the sample mean is an example of, it is coming from the sample, so it's going to be a statistic. Once it's coming from the sample, it's a statistic. Usually researchers are interested in what? In a phenomenon that is occurring where? That is occurring in the population. We always want to study, when we in the context of a population, we're interested in the population. And maybe in other, I'm not sure, but in experimental, those small experimental designs, even the inferences are made, and the inferences, when we make inferences, we infer to some population. Once we make inferences, we are inferring to some population. But when we study, we're interested in a population where something is happening. It can be a population of animals, but we're interested in a population where this thing that we are interested in, it's occurring there. And then the null hypothesis is about the population. It's about the population. And if you said a parameter, I can also take that, because when we specify the null hypothesis, we will have a population parameter. So we can take those ones. Then the alternate hypothesis is about same as the other one, because it's the opposite. And the null hypothesis is stated for the population. So it's the population and parameter. When we do null hypothesis, we are interested in the population. The sample only comes in as evidence that we use. It comes in as evidence that what we are estimating from the sample, we're using it as evidence. So with this number 10, I hope, because I was not able to paste the X bar correctly here in this in the quiz, but I hope you're able to see that it's supposed to be X bar. So which one is incorrect? Yes, the first one will be incorrect because it's X bar. We said X bar is about the sample. It's an average of, it's a sample average. So everything X bar would be incorrect because the null hypothesis is about the population. So, and then what else would be incorrect? It would be mu is greater than 0, right? Because that wouldn't be a null hypothesis. Null hypothesis is silent. So 1, 2, 4, and 5 would be incorrect because none of the above is not really applicable. The only correct thing here is mu is equals to 10, which is the population. It's equals to 0, which is the population average. The other one is its population average, but it's talking about the alternative. Remember, null hypothesis is quiet. It never says this is better, this is greater. It's silent. And then coming to the last part, type 1 error occurs when we incorrectly reject the null hypothesis. Remember here, I think you are allowed to select more than one. If we incorrectly reject the null hypothesis, if you selected that one is true, I can't see. Reject the null hypothesis when it's true. The last one, reject the null hypothesis when it's false. When we reject the null hypothesis when it's false, that's what we want. It's not an error. If we reject the null hypothesis when it's false, it's not an error. It's what we want. We want to reject it when it's false, right? If the null hypothesis says the methods are the same and they are not the same, we want to reject it. So it's not an error. Do not reject the null hypothesis when it's false. So the first one is incorrectly. If you selected that one, it's correct. And then when we reject it, when it's true, if we reject it when it's true. So when we reject it when it's true, we are saying there's a difference, when in actual fact, there is no difference. I hope it makes sense. So number 1 and 2, we're going towards the end. Number 2, type 2 error. So type 2 error, incorrectly reject the null hypothesis. No. Reject the null hypothesis when it's true. No. I've explained the third one. When it's false, we want to reject it, so it's not an error. It's about not rejecting. So the first error is we reject, and then there's a condition. The second error, we don't reject, and then there's a condition. They can be phrased in other ways, but the way I'm phrasing them is, first one is we reject, but we reject incorrectly. So we reject we reject the null hypothesis when it's true. The second error, we don't reject the null hypothesis when it is false. When it is false, we want to reject it. When we don't reject it when it's false, it's an error. It's a type 2 error. Then the last 2, level of significance, is probability of type 1 error, probability of type 2 error. So if you said 1 and you said 3, it's correct. It's denoted by alpha, yes, and it's a probability. I think it's important. It is a probability of type 1 error. It's not type 1 error, but it is the probability. The second last one, the power is related to, yes, it's related to, if you said both, it's correct. If you also said type 2, if you said both, it's correct, because with your type 2 error, we said that 1 minus the probability of type 2 error gives us the power. And it's also related to your type 1 error. Then the last point, if we increase the level of significance, what happens? If we increase the level of significance, yes, we are, I think the way I've stated it, it's saying like if we make it higher, right? When we say you increase the level of significance, you make it higher. But in actual fact, when we increase the level of significance, I think we want to say we actually want to reduce the error rate. So maybe the way I've put it, it's confusing. But when the level of significance, if we want the level of significance to be high, it means that our error rate, we are in actual fact decreasing our error rate. So for example, instead of using a 5%, maybe we will use a 1%. So that would increase the power of the test. Thank you for participating. And I think, yeah, we were able to maybe clear what was not clear. So now I'm going to proceed with the presentation. So at UNISA, we have SPSS as a software that we are using. There are others, there is also SARS, but the software that we as an office provide support on is SPSS. So some of the examples I'm going to use SPSS, and there are also, because we are doing sample size estimation, there are other tools that are available that are free. In this particular instance, I am going to be using, I will also use GPower, and the link to download the software is also provided. So for example, so in your study, if you are measuring a numerical variable, so let's say you are measuring IQ. If we go back to the example of IQ, and you have two groups that you are comparing, then your outcome is numerical. IQ is a number. So in terms of the analysis, so that's the other thing. In terms of the analysis that would be required, would be a t-test. So you can see these things, they integrate, that you understand your variable, that whether it is the type of measurement, whether it's categorical or it's numerical, and then you now also understand the analysis. Now that I have IQ and I want to compare it between two groups, then it means I need to do a t-test, because I have one numeric variable and I will have a categorical variable that has two levels. The null hypothesis will be that the IQ for the two groups is the same, and then we've seen the alternate. So using this example, so I'll use an example. Suppose I want to compare the calorie intake, average calorie intake of first-year students, right? So I want to compare the calorie intake. Now I want to compare by gender. So as I've said, some of the things you set them. So if I want to my level of significance to be 5% and the power to be 0.8, already I have these ones. These are the ones that I can set. I can also decide that I'm doing a two-tail or one-tail. And then what do I need now? What other things do I need? We know we need the variability, and we also need the effect size. If we are using the power analysis approach, I need the variability. So I need to know for these two groups, what is the variance in terms of this daily calorie intake. That is the variable of interest. So I need to know the variability for the one group and for the other group. So that's what I need. And the other thing that I need is the effect size. I need to know the difference that I would regard as practically significant. So you already have this. So what you could do is I could do a pilot, right? With a pilot, in terms of the guidelines to say 10, like I don't really have any set guidelines. I think it depends also on accessibility and resources. Some populations are big and very accessible, such that in your piloting, you have kind of room to select, to use, and whatever you are measuring is not resource intensive, because that's the other thing that sometimes you have access to the population is in that it's big and it's very accessible, but maybe the things you have to measure are quite intense. So a lot is involved in what you need to measure, such that you don't really have the resources to, your pilot really has to be kind of contained. So you can do a pilot. From the pilot, you'll be able to get your variability. You'll be able to, since you've collected data, you'll get the sample variance, because it's coming from the sample data, which is the pilot. You'll have the sample variance and for one group and the other group. And then you can also compute the effect size based on the pilot data. Or you can use the other methods that I've specified. You use what you know in terms of the effect size, what can be regarded as significant, then you can put that in. And in terms of the variability, maybe you can look at literature, other studies similar to yours, and draw from that. And the other option that was suggested was that you do your sample in phases. So you select a sample based on what you are getting from that sample, you input it, and you see if this sample is sufficient, if you need to add more respondents. So those are some of the options as to how you get these elements that you need to estimate the sample size. In this case, I used the pilot. So yeah, these are the parameters. I have my M1, the average for my first group, average second group, and I have the standard deviation, and I'm able to compute the effect size, right? I have the effect size, and then I can go into SPSS and actually estimate these things. With the SPSS, I'm not going to open it, but I've put the steps here that you will follow this. You go to analyze, because it's some form of analysis. It's a power analysis. We are trying to estimate the sample size using this approach. And now I'm estimating the sample size for an analysis that is about comparing means. So I will see. And in this example, my two groups are independent. The males and females, they are independent. If they were dependent, it would be the case where I measure, if we go to that example where you give people something for high blood pressure, and you measure their high blood pressure before you give them the treatment, and you measure it after. So you still have two groups. So data is for before, it's for after, but it's the same people, so it would be dependent. So you'll still have measurements from group 1, which would be before, and group 2, you can see it as after the treatment. That would be dependent. It's still a t-test, it would be dependent. In this example that we used here, we have two independent groups, so you would select independent samples. So I spoke about the inputs, the power, you specify it's 0.8. We have two groups. Here you can put 1 to have equal sample size, and then you put the things that you got from the pilot, the population mean, you get the standard deviation for the two groups. And then you also estimate, not estimate, you specify the level of significance. And then here you can specify whether it's a two-sided or one-sided. I've specified two-sided because I don't have any reason to test one direction. And then that would estimate the sample size for you. So you can see those elements that have been discussing, the power. If you are using this approach, you see this approach, you don't need to talk about the population size. No, you talk about the power, the level of significance. Now you go into the variable. to say what is the variability, and then you also get the average. And with this one, because you've put the average and the standard deviation, it's able to compute the effect size in the background, because the things that are required for the effect size have been given here. So it's giving you that your sample size would be 8. Given these things you have specified, if they change, the sample size will also change. So that is why you can't say 20%, 30%. I understand that in survey research, in survey studies, they sometimes have guidelines. Certain fields have guidelines, and those are followed in those fields. But generically, when we do sample size estimation, we use the information that is in line with this population that you are studying, such that if this input things that you are putting in, if they change, even this sample that is estimated will change. And then if we look at another example where now we are looking at, we're still comparing groups, because we remember we spoke about the effect size where we compare groups. Even here we are comparing groups. The only difference is that our data is categorical. So you have one group and then you have an outcome. So the null hypothesis would say that the two variables are independent, or that there is no association between the variables. Then your alternate hypothesis will say that they are dependent, or there's association. So you can see again here, the null hypothesis here is what is silent, and we want to use the data to reject it. But then in terms of what we are doing, the sample size estimation, we can use this example that I think the source somehow is not here. But yeah, I will add the source here. I got it from an article. I think I've referenced the article, but the source is not here. So suppose we have data that suggests that spontaneous incidence of tumors in old rats of a particular strain is 20%. So when we talk incidence, we talk proportion. We talk how many have this thing. So once you see, we talk about an incidence, we talk about a prevalence. So it's proportions. That's when you will think the chi-squared, because the chi-squared is about proportions, percentages. From percentages, we get those proportions. So as an experiment is set up to determine whether a chemical increases the incidence of tumors, right? Using the same strain of rats. So the researcher specifies that the incidence increases to 50%. Then they would like to have 80% of detecting this increase. So you have the power is set there, the alpha is set here. The one group, the P1 is 20%. Then the percentage in the other group is 50. The other things have been specified. So you see that the examples that I've done, what we use is specific to the problem and the population. So there is nothing that you can apply everywhere. You take things from, even when you take from another study, you have to apply your mind to say, is it applicable to my study? You know what, these inputs, are they applicable to my study? So in SPSS, as I've said, you go to analyze, it's power analysis. It's still, there are means, but now it's proportions. We are comparing proportions. So you'll specify the power, the ratio, and then the proportion have been given. We had 20% and we had 50%. The level of significance, the test as I've said, it would be a chi-squared test. So you specify the method of analysis, and then you are able to compute your sample size. So it's telling you that you're going to get 39 rats per group. So with each case, it's going to differ. So I'm doing a third example now. Now I'm doing Pearson's correlation coefficient, right? Pearson's correlation coefficient. Here we are looking at two numeric variables. We're looking at two numeric variables. It's a relationship. And the null hypothesis will say they are not related, meaning they are independent. The alternate will say they are related. So Pearson's correlation of coefficient, it measures a straight line relationship. So what you see on the left here, at the bottom, there is no evidence of a straight line relationship. The other two are giving you evidence. That's what Pearson's correlation coefficient looks at. So it's a number. That relationship is quantified through a number between 0 and 1. 1 indicating the relationship is strong. 0, the relationship is weak. So then the number that is measured will range between 0 and 1. So here, suppose we want to determine the correlation between the weight and height of grade 1 learners. So that's what we want to study. If we're using a power analysis approach, we don't need to know the population size. We need to know the power, right? We need to know the alpha, which we can set. And here is the correlation from that we are using as an input from previous studies. So maybe for the G power, which I will send, which we can also use, we can the G power is loaded. You can also use this G power tool. So here we are looking at correlation. It's different to the other one where we were comparing the groups. So we can use the G power. Now yes, here. So you can go to test to specify. Here we want correlation and regression, and we want correlation, bivariate, normal model, and then you specify. So G power also has a lot of material out there that you can read to also see when you are using it. If you want to do a t-test, what do you select? If you want to do a chi-squared, what do you select? I'm also showing it because it's a free tool. So in terms of what we want, if we want a two-tail, we want two-tail. The correlation from the previous study, we set it 0.6. And then the alpha, we can leave it at, and then the power, we want 80%. And then, and then we leave it as it. No, here it's going to be the 0.6 is supposed to be here. I'm not sure what was here, but this is the 0.6 has to be here. Why did I not put the effect size 0.3? Yes, so the 0.6, we will specify it here. So in terms of this, what we have, remember, it's based on what we specify. If from previous studies, the correlation was 0.7, then we would put 0.7. If it's 0.2, we would put 0.2. And that would influence. So let's say, for example, I'm talking about a weak and I calculate, you see now it's affecting the sample size. So the sample size is based on these elements that you are inputting, and they have to be as correct as possible. Wherever you are sourcing them, they have to talk to your population. They cannot just be you just take from anywhere. They have to talk to your population. And then the other example, so we've put this one, and then another example is if you are doing regression analysis, right? So you also want here, we start with one variable, which is like a simple linear regression. So we continue with our example of height. We want to look at the height, relationship between the height and the weight. Remember the correlation if we analyze it by just looking at the correlation, all we are able to say is that whether there's a strong correlation, linear correlation between the weight and the height. We're able to say when the weight goes up, the height also goes up. There is that positive relationship. Positive means they go in the same direction, meaning when the one variable goes up, the other variable, when X goes up, Y also goes up. When X goes down, Y also goes down. If it's negative, it's when X goes up, Y goes down. So they move in opposite directions. So if you take it to a simple linear regression, you're now also able to quantify by how much does the independent variable influence the dependent variable. With a correlation, you are able to say there's a strong correlation. If it's there, it's positive, you give a value. But when you now do a simple linear regression, you are able to now quantify and say the weight, it affects the height in this particular way. So when the weight increases by so much, by a kilo, the height increases by, or the other way around, maybe. Yes, when the height increases by, because these are maybe grade 1 learners, I'm not sure, maybe you'd want to measure them using centimeters. So when the height increases, maybe you will use your unit as 10 centimeters. When it increases by 10 centimeters, the weight increases in this particular way. So you're able to quantify. So using the G power for this example, so the only thing we are adding here is just now we're no longer doing a correlation, it's a simple linear regression. You can come now and look at the test, select the right test. It's gonna be a linear regression. Yes, you select a linear regression. And then let me see. Yes, no, I selected multiple. I need to select simple correlation. I'm selecting the wrong thing. Correlation. I am selecting the wrong thing. Let me see. Yes, we're supposed to select linear multi-fixed model. This one, linear multiple relation. Yeah, fixed model. Okay. Okay, multiple deviation from zero, the first one. Yes. That's the one that we have to be selecting. And then here, even though it says multiple, here you can specify the predictors. So because it's a simple linear, the predictor will be 1. The power is fine for it to be 0.8. The power is fine for it to be 0.8. And then we can specify the effect size. I don't think we've specified the effect size. Yes, the effect size, we might have got this from a previous study, or here if we say 0.35, we are saying we want a large effect. So you can see that everything is specific to the particular study. We could have also put what we are getting from what we got from a pilot or what we got. So you can see here, if you hover here, I'm not sure if it shows because it's small, you can see the conventions that you can also select here, the convention to say, do you want a small, a medium? Are you expecting a small, a medium, or a large effect? And then you can specify, or you can bring in the one that you have from your pilot or the one that you have from previous studies, and you can calculate, and it's giving you the estimated sample size. Here we just have one variable. So if we take the study further and we say it's the same study, but instead of having just a height as an independent variable, then maybe we can also have something around the diet. Maybe we can also have another variable, something around the diet, or maybe something, there are theories about breastfeeding and weight issues. So maybe you can have a variable as to whether the baby was breastfed or not breastfed as another independent variable. Whatever independent variable would be meaningful for the study, theoretically, then maybe you'll change here now to say, now I have 3 variables. Then you will have to calculate. So you see the sample size is now 36. But it's based on what we specified. And with regression, so you see, I've moved from simple to multiple. So if your study is doing multiple linear regression, I think this you've already seen that you can use this, and you can also do it in SPSS. I wanted to say with simple linear regression, there are guidelines, there are guidelines that if really you can't be able to estimate the sample size using these approaches, there are guidelines that talk about, as I said, 10 observations per variable that you are including. So if those guidelines are acceptable in your study, in your field, then you can follow those guidelines. But this is like a general way of estimating the sample size, that you input the analysis that you want to do, and you input the relevant elements, and then you estimate the sample size. So here we're following a power analysis approach. So we don't have to specify the population size. And then the next example, we're now going to look at examples of when we follow a precision-based approach. So if we follow a precision-based approach, we will need the margin of error. We've explained the margin of error is about precision. And then we have to specify the confidence level, the proportion, and the standard deviation. So this would be a formula for a single group, meaning that you are just estimating maybe a prevalence for a population. So you're just looking at one group. So maybe you're just looking at UNISA, the prevalence of something at UNISA. And then you can also have more than one group. The example here that we are using is prevalence. So we have a binary outcome. When we talk prevalence proportion, we have a binary outcome. Then we can use this example to try and follow. So a researcher wants to determine, I can maybe show it like this for now. A researcher wants to determine the impact of smoking during pregnancy on premature delivery. Normal pregnancies last about 40 weeks. And then those that occur before 37 weeks are regarded as premature deliveries. Then there is this study, which is the 2005 National Vital Statistics. It reported that approximately 12% of infants are born prematurely in the unit. So even with us here in South Africa, you will see that, for example, Statistics South Africa will have some of this, some things that they have figures for from their studies, sometimes from the census. So that information you can use. The only thing with, for example, Statistics SA, they don't do inferential statistics. So you might find that they have this, but they cannot tell you about the risk factors because they are not interested in the risk factors. They are interested in just providing those estimates. So you can take what you are getting from, and then now your study will be looking, you maybe want to look at some risks, the risk factors, right? Yes, you're looking at, you will be looking at smoking during pregnancy, and you'll be looking at premature delivery. So it's just two variables, but the same analysis can be extended to have more than two variables. And then once it has more than two variables, it will become a logistic regression because your outcome is binary. It's whether you gave birth prematurely or not. That's the outcome. Then here the risk here is whether you are a smoking mother or not a smoking mother. And then in this example, it's just a chi-squared analysis. But when you add more risk factors or more independent variables, it will become now a logistic regression model, such that now when you estimate the sample size, you will have to take into account that you no longer have one risk factor, you have more. And then you use, so the formula I showed it here, where it's N, then this is the proportion for group 1, proportion for group 2, and then you have the margin of error here, and then you will have the critical value. So if we finish off this, the investigator, they plans to collect data through medical records. So it's gonna be secondary data. They want a 95% confidence interval for the difference in proportion of infants born prematurely to women who smoke and those who do not. How many women should be enrolled in the study to ensure that 95%, we have that 95% confidence interval and a margin of error of 4. So these are specific to the study, right? You can see you can't just have a blanket approach. And then you can specify the different proportion and then estimate the sample size. So you can take 507 for those who smoke and those who do not smoke. And then if we following the precision-based approach for the for means now, I don't know what happened to my slide. Okay. So this would be the formula. You have the margin of error again. Here you have the standard deviation and the variability, and we still have our critical value. Let me check the time. So going back to our example here, the example is we have, there is a study, the researcher wants to look at the efficacy of a new drug to increase HDL cholesterol. This is the good cholesterol. They want to enroll participants and to assign them to receive either a new drug or a placebo. The measurement will be done after 12 weeks of the assigned treatment. Prior experience is telling them 10% of the participants will be lost to follow-up, and then 90 and will drop out of the study over 12 weeks. Then we want a 95%, and then we also would like a margin of error of not more than 3 units. So you see, these are specific to this particular study, and then you will specify them, and then you can apply the formula. I see that we have, 3 minutes. So you just have to input these parameters from here. You have your the 3, which is your what was specified as the 3 is the margin of error, and then we have which will be here will be the critical value, and then this other value we will get it from what was provided here. So I just want to conclude, I rushed this one. So in terms of, so for example, with your other survey research, there are also calculators which are more, they work well for survey research. Mostly with survey research, we would want the population size, and then we would want the what you are estimating, the level of proportion, and then the margin of error which you decide, and the confidence. So what tends to be the issue? The population size, most people can work around it and give you an indication. What tends to be an issue would be the proportion, to say, I'm studying job satisfaction. What am I going to put there? So as I've said, we usually use 0.5 when we don't have any thing that we can use that gives you the highest sample. So there's also non-response in survey. I want to come to it. It introduces bias. It's a big issue, and it can increase the variances since the actual sample is smaller than the one that we target. So we have this sample that we've estimated, but when we collect the data, a lot of people didn't respond. You might find that the people who responded have similar characteristics, right? You find that if you are in South Africa and you are doing your survey face-to-face, maybe the people who didn't respond are people from the high world areas. So your sample is now biased because the people who didn't respond have got similar attributes. And we can also oversample to account for that. So you will use you can be, when you plan your study, take into account what you are expecting, the non-response. Learn from previous studies to say, in this field, we usually get the response rate is around this range, or use a pilot, right? And then once you know, then you can factor it in. You can adjust your sample as indicated here. So here we are assuming a response rate of 60%. If we had estimated the sample size to be 120, then we would increase it to adjust for the non-response. Non-response also can also be adjusted after you've collected the data, but you can only adjust it when you your sampling scheme was a probability sampling approach, where you have a frame. So you can use the data from the frame to account for the non-response. But at a planning phase, when you are planning your sample size, you can take that into account to say, I'm doing a survey and I'm expecting this response rate Then I input my elements. This is the estimated sample size. When I account for this response rate, it's gonna be this much. I want to also count, I want to close with this one. This is about, in practice, when you estimate the sample size, you don't only have one variable in your study, you have more than one variable. So you need to take into account, if your outcome is categorical, the sample size required tends to be higher than the one for numerical. So if, for example, you have job satisfaction and you also have some background variables, if everything is important, the background variables are important, then you have to use the categorical variables to estimate the sample because they are more sample intense, yeah, compared to the numeric. So, or the other approach is when you have variables, you select the variables that are important in your study, and you can estimate the sample size for each based on the analysis that you would want to do. And then once you've estimated, you can now rank and see. Sometimes if for the ends that you've estimated are close to each other, you can just select the biggest one. So if the ends are close to each other, as I'm saying, you can select the biggest one. Sometimes they can vary so much, such that it's very difficult to select one. And there are also budget constraints. So you'll have to take that into account. In other cases, you might find that the variables that you want to include, they require so much sample that you might have to let them go. So when you have many variables, the sample, you accommodate the important variables. So as I say, you can estimate depending on the analysis that you want to do, but you must ensure that the important variables that you will be mainly reporting on as your key are accommodated. Yeah, so I've indicated this, that sometimes you find that when you have different variables, you're not able to accommodate all of them because they are giving you a very different sample size. For this, to analyze this variable, you are getting this sample size. To do this one, you are getting this one. And they are just not in sync, such that you now have to see, can I keep all of them? And if I keep all of them, it means I will go with this big sample. Do I have the resources, or do I let this variable go because it's the one that is, or I will not make it important? Yes, I keep it, but it's no longer going to be a key variable, those decisions. And then I'm just concluding. I think we've covered this. These are some considerations, and we've covered all of them. And you can maybe run through them when you have time. I thank you.